In the unending, silent dark, where the constellations of human myth dissolve into an anonymous sea of stars, humanity has opened its most powerful eye. It is an intricate machine of gold-plated beryllium, a colossal mechanical sunflower sailing on solar winds 1,000,000 miles from the warmth and light of home. It exists in a state of perpetual cold, colder than the surface of Pluto. A sentinel built for one extraordinary purpose: to look back to the dawn of time and listen for the whispers of the cosmos. For all of our recorded history, through every age and every empire, we have stared into that silent, indifferent abyss and asked one unifying, essential question. A question that has driven our art, our science, our philosophy, and haunted the quietest moments of our existence since we first understood the vastness of the night sky. Are we alone? The message arrived not with a thunderous announcement, but as a quiet stream of data on a cold Tuesday morning in December. It was a ghost in the machine, a signal buried in an avalanche of numbers, terabytes of infrared light that had faithfully traveled for 120 years across the unforgiving vacuum of interstellar space. In Cambridge University, a scientist named Niku Madhusudan sat before his monitor, watching the spectral lines resolve into a pattern. What he was seeing, it shouldn't exist. It was a chemical signature so profoundly strange, so uniquely and inextricably tied to the processes of biology, that it defied all known non-living chemistry. His hands, it is said, began to tremble. This was no faint anomaly. The signal was robust, clear, and persistent. The probability of it being a random fluke of cosmic noise or an instrumental error was calculated to be less than 3 in 1,000. This led scientists, a community renowned for its caution and skepticism, to attach a number to what may be the single most profound discovery in human history: 99.7% certainty. This isn't a hunch. This isn't a hope. It is a 3 sigma detection, the same level of statistical confidence that physicists required to announce the discovery of the Higgs boson, the same mathematical proof that validated Einstein's theory of gravitational waves. It is a number that transforms speculation into established science. They had found a world, a planet in the deep sky constellation of Leo, designated K2-18b. It is a world vastly larger than our own, with a gravitational pull that would crush a human frame, and it is wrapped in an atmosphere that would be a lethal poison to us. And yet, the data insists that this alien world may be more fundamentally habitable than Earth itself, a world where the global temperature is held in a perfect, life-giving equilibrium of 120 degrees Fahrenheit, and where the air itself pulses with a molecule that on our home planet is only ever produced by one thing: life. We are standing at the precipice of a new reality, on the threshold of a discovery so monumental it will inevitably divide the timeline of our species into 2 distinct eras: the long, lonely age when we believed we were alone in the universe, and the new unknown future where we know we are not. The journey to understand this discovery is not just a scientific exploration. It is a journey into the very heart of what it means to be alive. It will challenge our most fundamental assumptions about habitable worlds, about the nature of the stars in our sky, and about our own fragile place in this vast, complex, and breathing universe. The age of cosmic loneliness is over. Let's begin. To truly comprehend the significance of K2-18b, we must first be willing to deconstruct our Earth-centric biases. For generations, the scientific consensus held that the search for extraterrestrial life was, fundamentally, a search for a mirror. We were looking for Earth's twin. The checklist was specific and non-negotiable: a rocky planet, roughly 1 Earth mass, orbiting a stable, sun-like star, and it had to exist within a narrow band of space called the circumstellar habitable zone, more poetically known as the Goldilocks zone. This is the orbital region where temperatures are not too hot and not too cold, but just right for liquid water to pool on a planet's surface. For decades, this was the template, the holy grail of astrobiology. K2-18b has taken that template and shattered it into a million pieces. This planet is not Earth's twin. It is something far stranger, and perhaps far more promising. It belongs to a now common class of exoplanets known as super-Earths, worlds that are larger and more massive than our own, yet significantly smaller than the ice giants of our outer solar system, like Neptune or Uranus. For many years, the astronomical community largely dismissed these planets as inhospitable. The conventional wisdom suggested they were likely to be mini Neptunes, planets with no solid surface, just a crushing gas envelope over a high-pressure core of exotic ices and rock. Their immense gravity and dense, suffocating atmospheres were considered a death sentence for life as we know it. We weren't seriously looking for life there. K2-18b has forced us, with the sheer weight of its evidence, to completely and utterly reimagine what a habitable world can look like. Let's consider the sheer scale of this world. It is a behemoth, weighing in at 8.6 times the mass of the Earth. Its diameter is more than twice that of our planet. The consequences of this mass are profound. The surface gravity on K2-18b is nearly 3 times stronger than what you are experiencing right now. A person weighing 150 pounds on Earth would be immobilized under an oppressive weight of over 400 pounds. At first, this seems unequivocally hostile, but in the grand cosmic chess game of planetary survival, this crushing weight is a decisive, life-preserving advantage. This intense gravity holds the planet's atmosphere with an unyielding grip. To understand why this is so crucial, we need only look at the tragic history of our neighbor, Mars. The red planet was not always the frozen, barren desert we see today. Billions of years ago, it was a water world with rivers, vast lakes, and perhaps even shallow oceans. It had a thicker atmosphere and a warmer climate. But Mars is small. With a weak gravitational field, it could not hold on to its atmospheric blanket. Over geological time, the relentless solar wind, a stream of charged particles from the sun, stripped that atmosphere away molecule by molecule, bleeding it out into the blackness of space. As the air thinned, the water either froze or evaporated, and Mars died. On K2-18b, that kind of atmospheric escape is impossible. Its thick, dense atmosphere is anchored in place by a gravitational well so deep that even the most violent stellar flares from its host star cannot strip it away. It possesses a permanent, stable shield against the hazards of space, a shield that can endure for eons. And what an atmosphere it is! It defies every biology textbook we have ever written. Instead of the familiar mixture of 78% nitrogen and 21% oxygen that we breathe, the air on K2-18b is overwhelmingly dominated by hydrogen and helium, the lightest and most abundant elements in the universe. On Earth, hydrogen is a forgotten trace gas, making up less than 1 part per million of our air. On K2-18b, hydrogen is the main event. It forms a vast, thick envelope that shrouds the entire planet. For decades, we believed such a hydrogen-rich atmosphere was completely incompatible with life, but we were profoundly wrong. This hydrogen blanket is the very engine of the planet's habitability. It creates a greenhouse effect so perfect, so incredibly stable that it maintains a constant, life-friendly temperature across the entire surface of the globe. It is a planetary thermostat of unparalleled efficiency. This remarkable world orbits a star named K2-18, a red dwarf. These stars are the quiet, unassuming workhorses of the cosmos. They are the most common type of star in our galaxy, making up a staggering 3/4 of the entire stellar population. They are much smaller, significantly cooler, and far dimmer than our own sun. But they possess one incredible, almost magical advantage: time. Our sun is a middle-aged star, currently about 4.6 billion years old, with a total lifespan of roughly 10 billion years. In its old age, it will swell into a red giant, a monstrous bloated star that will boil away our oceans and incinerate the inner planets. Red dwarfs, by contrast, are cosmic marathon runners. They are frugal with their nuclear fuel, burning it so slowly and efficiently that they can shine with a steady, stable light for trillions of years. That is a timescale so vast it beggars belief, 1,000 times longer than the current age of the entire universe. Any life that evolved on K2-18b would have a virtually unlimited amount of time to develop. On Earth, it took nearly 4 billion years for life to evolve from simple, single-celled organisms to the complexity we see today. On K2-18b, life would have an almost eternal stage on which to perform its evolutionary play. It has a stable, never-ending star, a permanent atmosphere that can't be stripped away, and, as the James Webb Telescope discovered, it is saturated with all the right ingredients for a thriving, global, biological paradise.
So, how did we unlock the secrets of a world 120 light-years away? How did we listen to the whisper of its atmosphere across such an immense gulf of space and time? The answer lies in a brilliant and painstakingly delicate observational technique. We know that K2-18b orbits its star once every 33 Earth days. From our specific vantage point in the cosmos, this orbit is aligned perfectly edge-on. This means that, like clockwork, every 33 days the planet passes directly in front of its star in an event we call a transit. During this transit, which lasts for several hours, a tiny, almost infinitesimal fraction of the starlight must filter through the planet's upper atmosphere before continuing its long journey towards Earth. For 120 years, that specific light traveled, carrying with it a hidden message, a chemical story written in the language of physics. Locked within that faint beam of starlight is the atmospheric fingerprint of K2-18b, a technique known as transmission spectroscopy. The physics behind it is both simple and elegant. Every molecule, whether it's water, methane, or carbon dioxide, has a unique property. It absorbs very specific wavelengths or colors of light. Water vapor, for example, absorbs certain bands of infrared light, while methane absorbs others. Think of it like a barcode. When the pristine, full-spectrum light from the star K2-18 passes through the planet's atmosphere, the molecules within that atmosphere act like a filter, absorbing their characteristic colors and leaving dark lines, absorption lines, in the light's spectrum. When that light, now imprinted with the planet's atmospheric barcode, finally reaches the 21-foot gold-coated primary mirror of the James Webb Space Telescope, we can analyze precisely which colors are missing. By reading this cosmic barcode, we can determine exactly what K2-18b's atmosphere is made of. The technical challenge of this feat is almost incomprehensible. The parent star, K2-18, is billions of times brighter than the faint reflected light from the planet orbiting it.
Isolating the light that passed through the planet's thin atmospheric rim is like trying to detect the subtle change in color of a searchlight's beam caused by a single firefly hovering at its edge while viewing it from 1,000 miles away. This is the precise task the Webb telescope was designed and built to accomplish. Its instruments are cooled to near absolute zero to eliminate their own heat, making them so sensitive that, as the analogy goes, they could detect the faint heat signature of a bumblebee on the surface of the moon. For months, Niku Madhusudan's team at Cambridge patiently observed the world. Each 33-day transit was another opportunity to gather photons, to build up the signal and reduce the noise. Slowly, a picture began to emerge. The first transit data confirmed the unmistakable signature of water vapor. This was a monumental discovery in itself, confirming the presence of water, a critical prerequisite for life, on a world outside our solar system. But it was not definitive proof of life. Next came the clear detections of both methane and carbon dioxide. This was even more intriguing. On Earth, these gases are intimately connected to life, key components of a global metabolism that cycles essential elements through the air, the land, and the oceans. The pieces of an extraordinary puzzle were beginning to fall into place, and then as they refined the data and looked deeper into the faintest signals, they found the smoking gun. Dimethyl sulfide, CH3-2S. The name may sound like a sterile entry in a chemistry textbook, but these three words, this simple molecule, may represent the single most important scientific discovery in the history of mankind. On planet Earth, after billions of years of geological and chemical evolution, we know of only one source for dimethyl sulfide: life. It is produced exclusively by living organisms. In our oceans, vast blooms of phytoplankton, the microscopic floating plants that form the base of the marine food web, create this molecule as a byproduct of their metabolic processes. Certain types of marine bacteria, specific kinds of algae, and even some terrestrial plants release it into the atmosphere as part of their normal biological functions. But no known geological process creates it in any significant quantity. No non-living chemical reaction in a planet's atmosphere or on its surface has ever been observed producing this specific molecule. It is not like oxygen, which can be created by the splitting of water molecules by ultraviolet light. It is not like methane, which can leak from geological formations or be produced by volcanoes. Dimethyl sulfide has no known abiotic source. Its existence is a direct, unambiguous pointer to biological machinery. Finding it in the atmosphere of an alien world is the astrobiological equivalent of discovering a pyramid on Mars. The implication is so powerful, so direct, that it is almost impossible to logically ignore. It is what scientists have spent their careers dreaming of finding: a robust, credible biosignature, the fingerprint of biology itself. And this was not a faint borderline detection. The signal was so strong, so clear, and statistically significant that it could only mean that biological processes on K2-18b are not just present, they are thriving on a colossal planetary scale. We're not talking about a handful of microbes clinging to life in a single hydrothermal vent. We're talking about a biosphere so vast, so productive, and so globally integrated that it is actively changing the chemistry of its entire world's atmosphere. It is pumping out a biological gas in quantities so enormous that we can detect its signature from over 250 miles away.
The chemical structure of dimethyl sulfide itself tells a story of profound biological complexity. It is a molecule that requires specific, specialized enzymes to be constructed, intricate biological machinery that evolved on Earth over billions of years as part of the global sulfur cycle. The fact that a similar molecule exists on K2-18b strongly suggests that life there has also evolved sophisticated and targeted biochemical pathways. It hints at the tantalizing possibility of a universal chemistry for life, a common molecular blueprint that is written into the very laws of physics and chemistry, ready to emerge wherever the conditions are right. And perhaps just as shocking and revealing was what the telescope didn't find. The established chemical models for a massive world with a hydrogen-rich atmosphere, like a mini Neptune, all predicted that it should be rich in ammonia. Ammonia is a simple, stable molecule that should be abundant in such an environment. Yet the spectrum from K2-18b showed a suspicious and significant lack of it. This is another powerful piece of evidence. The absence of an expected chemical can be just as telling as the presence of an unexpected one. It strongly suggests that biological processes on the planet are actively consuming the ammonia, removing it from the atmosphere as part of their metabolic cycle. Life isn't just a passive resident on this world. It is an active, dynamic force, shaping its own environment, consuming some chemicals and expelling others, creating a planetary-scale metabolism. The atmospheric fingerprint of K2-18b is not that of a dead, static chemical equilibrium. It is the signature of a world that is, in a very real sense, breathing. This chain of discoveries forces us to confront a staggering, almost heretical possibility. For all of Earth's undeniable beauty, for all its breathtaking biodiversity, it might not be the ideal cradle for life in the universe. In many ways, K2-18b could be fundamentally better. Its perfect, stable temperature is a central piece of this incredible puzzle. The Webb telescope didn't just estimate this temperature, it measured it with a precision that is hard to fathom across interstellar distances, 120 degrees Fahrenheit or about 49 degrees Celsius. To us, that might sound uncomfortably hot, like a summer afternoon in Death Valley, but for biology, it could be a paradise. Temperature is the master variable for life. Too cold, and water freezes into inert ice, stopping the complex chemical reactions that life depends upon. Too hot, and water boils away into steam, leaving behind a sterile, lifeless desert. The delicate range where liquid water can exist, the habitable zone, is surprisingly narrow. Earth sits comfortably within this zone around our sun, a remarkable stroke of cosmic luck that has allowed life to flourish for billions of years. But K2-18b's perfect temperature is not an accident of orbital mechanics alone. It is the result of a finely tuned, symbiotic relationship between the planet, its atmosphere, and its star. The planet orbits its cool red dwarf star at a very close distance, much closer than Mercury is to our sun. This close orbit means it receives almost exactly the same amount of energy per square meter as Earth gets from our much larger, hotter sun. But its true secret weapon is its thick hydrogen atmosphere. This planetary blanket is a masterful insulator. It traps the infrared radiation, the heat, emanating from the planet's surface, creating a powerful greenhouse effect that keeps the entire globe warm. Crucially, it keeps it stable. On Earth, we are subject to dramatic and often violent temperature swings. The difference between day and night can be tens of degrees. The change between summer and winter can be extreme. The frozen poles stand in stark contrast to the boiling equator. These variations create enormous stress on living organisms, forcing them to develop complex adaptations, hibernation, migration, fur, feathers, just to survive the changing conditions. On K2-18b, the thick atmosphere acts like a global circulatory system, redistributing heat from the star-facing side to the dark side with incredible efficiency. The side of the planet locked in perpetual, eternal darkness is thought to be just as warm and habitable as the side that lives in permanent daylight. Imagine a world with no winter, no ice caps, no deadly temperature extremes. A world where every single corner of the globe is a habitable, comfortable, stable environment. Life on such a world would not need to waste precious energy on mere survival. It could invest all of its resources into growth, reproduction, and the relentless upward climb of evolution. Furthermore, that 120-degree temperature falls squarely within a known biological sweet spot. Laboratory experiments have confirmed that life as we know it can thrive and even prefers such conditions. Thermophilic, or heat-loving organisms on Earth flourish in the hot springs of Yellowstone or around deep-sea hydrothermal vents at similar temperatures. At this temperature, chemical reactions proceed rapidly, supporting a complex and energetic metabolism, yet it remains cool enough to prevent the catastrophic breakdown of essential biological molecules like DNA and proteins. The discovery of K2-18b's perfect stable temperature isn't just a scientific curiosity. It's compelling evidence that the universe can create conditions for life that are not merely habitable, but potentially more hospitable, more stable, and more conducive to long-term evolution than our own cherished Earth.
Beneath this remarkable hydrogen-rich atmosphere and held at this perfect global temperature lies the most tantalizing possibility of all, a global ocean. Many scientists now believe that K2-18b is a prime candidate for a Hycean world, a theoretical class of planet defined by a deep liquid water ocean lying beneath a hydrogen-rich atmosphere. Such a world would be unlike anything we have ever seen, a water world of unimaginable proportions. This ocean would not be made of pure water like ours. The immense atmospheric pressure at the surface would cause the atmospheric hydrogen to dissolve directly into the liquid water, creating a unique hydrogen-enriched ocean. This solution has properties that make it even more stable for life than pure water. It can remain liquid across a much wider range of temperatures and pressures. This solves one of the greatest long-term challenges for a habitable world: atmospheric loss. On K2-18b, the global ocean would act as a colossal atmospheric reservoir. Over trillions of years, as some hydrogen inevitably escapes to space from the top of the atmosphere, more would simply and steadily dissolve out of the ocean to replace it, maintaining a stable, protective atmosphere for a timescale that dwarfs the entire history of Earth. The very chemistry of this unique ocean opens up entirely new and alien possibilities for life. Hydrogen is a potent chemical energy source. On Earth, certain microbes in oxygen-starved environments can metabolize hydrogen, but it's a niche strategy due to the scarcity of hydrogen in our atmosphere. On K2-18b, with an ocean saturated with it, hydrogen could be the primary fuel for life. Entire ecosystems of organisms could evolve to breathe the ocean itself, deriving their energy from the dissolved hydrogen in a world where their main source of fuel is essentially unlimited and ubiquitous. The sheer physical scale of this potential ocean is difficult for the human mind to process. Computer models based on the planet's mass and density suggest this ocean could be hundreds or perhaps even thousands of miles deep. To put that into perspective, the deepest point in Earth's oceans, the Mariana Trench, is about 7 miles down. All of Earth's oceans combined, the Pacific, the Atlantic, the Indian, the Arctic, would be a mere shallow pond in comparison to the globe-spanning deep ocean of K2-18b. This vast, stable, energy-rich aquatic environment, protected from any potential stellar flares by miles and miles of water above, could harbor ecosystems of a complexity and diversity that would make Earth's biosphere seem limited by comparison. We have long dreamed of finding life on other worlds. We often imagined it as something fragile, clinging to existence on the knife's edge of possibility in a hostile universe. But K2-18b suggests a completely different, more optimistic reality. A universe where the most life-friendly environments are the ones that are most alien to our own experience. A world where a hydrogen sky meets a global, energy-rich ocean perfectly and perpetually warmed for trillions of years by a stable, never-ending star. This brings us to another key piece of evidence derived from the source material, a fascinating aside that paints a broader picture of how common such worlds might be. The discovery did not happen in a vacuum. It was part of a larger survey, a systematic hunt that is revealing a universe far more populated with habitable real estate than we ever dared to imagine. Within a relatively tiny sphere of just 200 light-years around Earth, astronomers are now identifying a rapidly growing catalog of over 50 planets that show at least some signs of potential habitability. These are not just distant, fuzzy maybes. These are our local neighbors.
This galactic neighborhood is surprisingly diverse. It contains more super-Earths like K2-18b, smaller, rocky planets orbiting in the habitable zones of other red dwarfs, and even worlds that might have global ice coverage but harbor vast subsurface oceans kept liquid by internal heat, much like Jupiter's moon Europa or Saturn's moon Enceladus. Each of these worlds represents a different experiment in planetary evolution, a unique set of conditions that could give rise to life entirely unlike our own. The statistical implications are breathtaking. If our small local corner of the Milky Way contains dozens of potentially life-bearing worlds, then the entire galaxy, with its 400 billion stars, could be home to billions upon billions of planets where life could exist. We may live in a galaxy that is fundamentally, intrinsically alive. The silent hero of this entire story, the magnificent instrument that made this discovery possible, is a triumph of human ingenuity and relentless ambition: the James Webb Space Telescope. To call it a successor to the Hubble Space Telescope is a profound understatement. It represents a quantum leap in our ability to perceive the universe. It does not orbit the Earth. Instead, it is stationed in a lonely, distant orbit around the Sun at a point of gravitational stability called Lagrange Point 2, or L2, nearly 1 million miles beyond the Moon. From this vantage point, its massive sun shield, the size of a tennis court and made of 5 layers of a material called kapton, can permanently block all heat and contaminating light from the Sun, the Earth, and the Moon. This feat of engineering allows the telescope's sensitive instruments to cool down to their operational temperatures of just a few degrees above absolute zero, minus 450 degrees Fahrenheit. This extreme cold is essential because the Webb is an infrared telescope. It sees the universe in light that is invisible to our eyes, the light of heat. Everything that is warm emits infrared light, including the telescope itself. By being so cold, the Webb is practically invisible to itself, allowing it to detect the fantastically faint infrared signals from the most distant objects in the universe. Infrared light is the key to unlocking cosmic secrets. It can pierce through the dense, opaque clouds of cosmic dust and gas that hide the birthplaces of stars and planets. And most importantly for our story, it is the specific part of the spectrum that carries the clearest chemical fingerprints of alien atmospheres. The telescope's primary mirror is an icon of 21st century science. It is a breathtaking 21 feet across, composed of 18 perfect hexagonal segments. These segments are made of beryllium, a metal that is both incredibly strong and exceptionally lightweight, and then they are coated with a microscopically thin layer of pure gold. Gold was chosen because it is exceptionally reflective of the long wavelength infrared light that Webb is designed to see. When these 18 segments are perfectly aligned by tiny motors to a precision of a few nanometers, they function as a single, colossal, flawless mirror, gathering photons that have been traveling through space since the beginning of time. But to find the biosignatures on K2-18b, the telescope had to perform its most difficult and delicate feat of cosmic magic. It had to somehow block out the overwhelming, blinding glare of the host star. To accomplish this, it uses a suite of advanced technologies called coronagraphs. Originally invented to study our own sun's faint outer atmosphere, the corona, which is normally invisible against the sun's brilliant surface, Webb's coronagraphs are systems of precisely shaped internal masks and occulting spots that can be moved into the light path to physically blot out the starlight. This allows the much, much fainter light from a nearby planet's atmosphere to pass through and reach the detectors. Once this light is collected,
the work is far from over. The raw data is filled with noise and artifacts. Advanced artificial intelligence and machine learning algorithms, developed over years by teams of scientists and engineers, must then go to work. They analyze millions upon millions of data points, meticulously distinguishing the genuine planetary signal from tiny imperfections in the telescope's optics, stray light, and the inherent randomness of deep space. The entire process is like using a sophisticated digital filter to remove the deafening roar of a jet engine so that you can isolate and analyze a single, quiet whisper hidden underneath. That whisper, carried on a handful of photons that have faithfully journeyed for 120 years, contains the revolutionary secret of life on another world. The discovery of biosignatures on K2-18b represents not just a triumph of scientific theory, but a testament to our species' ability to build machines that can ask the deepest questions of the cosmos and receive an answer. We are no longer just wondering if life exists elsewhere. With this telescope, we are actively, directly watching it breathe.
For the entirety of our species' existence, for every civilization that has risen and fallen, for every human who has ever lived and died, our existence has been defined by a profound and pervasive sense of cosmic loneliness. We have looked out into the silent, star-dusted blackness of the night and seen only a beautiful, terrifying, and profound emptiness. That era of our history is now drawing to a definitive close. The discovery on K2-18b, with its peer-reviewed, scientifically robust 99.7% confidence, is the beginning of a paradigm shift in our understanding of the universe and our place within it. We are discovering that the galaxy isn't just home to a few scattered, miraculous oases of life like Earth. Instead, it appears to be teeming with planets that could support it. The humble red dwarf stars, like K2-18, once largely ignored in the search for life due to their dimness and propensity for flares, are now considered prime targets. Since they make up the vast majority of stars in the galaxy, this single finding exponentially increases the number of potentially habitable worlds in the Milky Way by hundreds, if not thousands of times. The number of potential homes for life just exploded. The Milky Way, with its estimated 400 billion stars, could be home to billions, perhaps tens of billions of living worlds. Each of these worlds represents a different solution to the challenge of life, a different experiment in evolution. Some might have evolved oxygen-rich atmospheres, like ours, supporting complex multicellular organisms that breathe and photosynthesize. Others, like K2-18b, might have developed a thriving biosphere based on hydrogen chemistry, creating ecosystems that would seem utterly alien and magical to us. And some, undoubtedly, will have taken evolutionary paths so bizarre and unexpected that we have not yet even developed the imagination to conceive of them. This has profound and immediate implications for the search for extraterrestrial intelligence, or SETI. If life itself is common, then it becomes statistically more probable that intelligent technological life might be equally widespread. The giant radio telescopes that have been patiently scanning the skies for decades, listening for signals from alien civilizations, may not have to search for much longer. The question is subtly but powerfully shifting from, are they out there, to how many are out there, and what form have they taken? The great silence of the universe might not be a sign of emptiness, but a sign of our own technological infancy. Perhaps most remarkably, the finite speed of light gives us a strange and poignant connection to this world. The 120 light-year distance to K2-18b means that the light we are detecting today left that planet around the year 1905. We are seeing the breath of alien life from a time when Theodore Roosevelt was president, and the Wright brothers had only recently made their first flight. Conversely, it also means that if there is an intelligent civilization on that world with telescopes of their own, they could be detecting the chemical signs of life on Earth right now. Our earliest powerful radio and television broadcasts, which left Earth about a century ago, are just now washing over their planetary system. We are not just discovering life on a distant world. We may be in the process of making first contact, a silent, unknowing conversation held across the vast, dark emptiness between the stars. The moment will come, perhaps quietly in a university lab or a NASA data center, when the statistical confidence of this or a similar discovery rises from 99.7% to 99.999%, and then to a certainty beyond any reasonable doubt. In that instant, everything we think we know will change. Science, philosophy, theology, and art will all be transformed as we grapple with the concrete reality that biology is not a divine miracle unique to Earth, but a fundamental and common feature of the cosmos. Every child born after that moment will grow up with a completely different understanding of the universe. They will know that we are part of a vast cosmic community of living worlds, each following its own unique evolutionary path, but all sharing the fundamental experience of life. The universe will be transformed in our perception, from a vast, empty, sterile space into a thriving, dynamic cosmic ecosystem, teeming with biological activity and endless evolutionary experimentation. The James Webb Space Telescope has given us the first definitive, tantalizing clue. It has peered across the void and found a world wrapped in hydrogen clouds and warmed to a perfect, stable 120 degrees Fahrenheit. A world where the air is filled with a molecule that can only come from the intricate machinery of life. We are no longer alone. The more profound truth may be that we never were. The universe has been teeming with life all along, patiently waiting for us to evolve and to build an eye sharp enough and sensitive enough to finally see what was always there. A cosmos that is fundamentally, breathtakingly alive with possibilities we are only just beginning to imagine.